So, welcome to another exciting biomedical image processing class. In our last exciting biomedical image processing class, we did a little work on filtering. We've also talked a little bit about convolution. In this class, we're going to continue that discussion, but we're going to work up to edge detection. And in this edge detection, where we're going is to get a single pixel width-wide edge. And let me tell you why I think that's so important. We have a new laser cutter, and the laser cutter will cut a single pixel width-wide edge directly into plastic. And I thought, gee, wouldn't it be swell if we could write a program to drive our laser cutter? And so what I'd like to be able to do is have you guys take a picture of something cool and then cut it into plastic. But if you use your cameras or your cell phones or your webcams or whatever to take this picture, you're going to have to figure out how to make a decent edge out of it before you cut it into plastic. In other words, this is not going to be one of those how do we call it? Pieces of software you can go out and buy at Egghead Software. It'll have to be a piece of software that you write custom to make a single pixel width-wide edge that looks good. And so therein lies, I think, the rub. What makes a good edge? And one of the things that I have found in image processing is that image processing is really very good at looking at little pixels and trying to figure out how they're different from other little pixels. And this is one of those things that really kind of gets my goat. Image processing filters are able to detect sudden changes in energy. And sudden changes in energy are said to be good edges, according to low-level image processing filters. But the way your brain sees edges is really different. And the reason why it's different is because your brain is an expert at finding edges. Your brain says this is a good edge and that's not a good edge because of what your brain knows about edges. So, for example, if you see a shadow being cast by the edge of a window, you say, well, that's not the good edge. Even though the computer says, aha, a sudden change of energy. Ooh, look, a good edge. Your brain has no trouble saying, look, it's just a shadow. That's not the interesting edge. The interesting edge is actually the edge of the window. So the real question is, how do you know a good edge when you see it, and how do you tell the computer that this is a good edge? And that is a very interesting and important question, especially for biomedical imaging. Because in biomedical imaging, what might look like nothing more than a simple shadow could be scar tissue. And if you've opened up somebody's brain and you start to discover scar tissue, you could be in trouble in the middle of an operation. And that's really bad. So one of the things people like to do when they go and they take a series of x-rays, slices, if you will, of a human organ like the brain, is they try to assemble those x-rays and see in 3D what those shadows look like. And if they're more than just a simple artifact of digitization, if those shadows are actually something that you need to pay attention to when you're in the middle of an operation, it's really good to know about those things. So I thought it would be good for us to start with some basic ideas. So let's go back and think in terms of the basics. We've been talking a little bit about filtering, and when we talked about filtering in the past, what we talked about was a kind of two-dimensional matrix that was multiplied against the pixels underneath, and then we would add up all the numbers and replace one pixel with that number, and then we would take that entire matrix and we would shove it over by maybe one column and repeat, right? And if we did that for every single pixel, it was called convolution. And so we called the convolution a sliding window dot product. And with that sliding window dot product, we were able to create a whole series of different filters. High pass filters, low pass filters, band pass filters, and in fact we can do edge detection filters, as I will show you shortly. And so one of the things I wanted to do was just kind of review some of the pictures that we've seen before. The low pass filter is just a simple averaging filter. It gives us a little bit of blur because what it's doing is it's taking out the high frequency stuff and leaving out the low frequency stuff. We talked a little bit about scaling filters. I like it when we have what are called unity gain filters. Unity gain filters are such that they don't change the overall brightness of the image, but instead what they do is they change the underlying detail available in the image. And one way in which we can do that, I'll call it unity gain filters, is we can add up all of the elements inside of the matrix and then divide through by the sum of those elements. So in this case, if you look at all the elements in the matrix for this little low-pass filter and you add them up, it adds up to 20. So I divide the whole thing by 20, and then what happens is you have what's called unity gain. So you can still change the underlying details of the image without, I'll call it, altering the overall brightness of the image. And that becomes kind of an important feature, because if what you wanted to do was make the image brighter, we have ways of doing that. If you wanted to make the image darker, well, we could do that too. But that's not what we wanted to do with this kind of filtering, and it's, I think, patently obvious that that's a bad thing, changing the overall brightness of the image without wanting to do it. You know, if you want to do it, fine, we can do it. But let's not do that just as a matter of course, because if we start doing that, then as we low-pass filter the image repeatedly, it'll get brighter and brighter and brighter, and pretty soon we won't have any dynamic range left. For Gaussian filters, all we've done is we've imposed a kind of a function that has a nice, smooth bell curve, and that's it. And one thing you can do with that nice, smooth bell curve is you can spread out the bell, and that's called the standard deviation. And you can also narrow down the bell, right? And so one of the things you can see about the bell curve is you can see whether or not it has a long tail or not, right? So when you spread out the bell curve, you're basically taking the tail and you're making it a little less long, and you're making more of the bell cover more of the tail. And if you do that in 2D, you can change the center of that bell curve, and that's what the x sub c, y sub c part is for. And the reason why you like to do that is because bell curves for Gaussians are typically centered at the origin. And centering a curve at the origin is a very fine thing if you're a mathematician. But if you're doing image processing, you really don't want it centered at the origin, because the origin is the upper left corner of your image. What you really want to do is you want to center it at the image. And if the image is going from 0 to 255 in width and 0 to 255 in height, well, it would be swell to take 255, cut it in half, call it 128, and say, okay, let's center the bell curve at 128, and then you got the little bell curve right at the center of the image. And so that's why you put in the little x sub c, y sub c. And then if you want to, you can adjust the standard deviation. And when you think about it, what you're really doing with this nice, smooth, Gaussian function, if you want to turn it into like a matrix of 2 by 2 numbers, is you have to digitize it. In other words, you're resampling the nice continuous function. Think about it a different way. Suppose you had a sine wave, and you wanted to take the sine wave, math.sine, and you wanted to put it into an array. Let's say the array had 255 elements, right? What would you do? Well, look, sine waves go from 0 to 2 pi. I would make a dilation parameter that, let's say, goes from 0 to 1, and it does it in increments of 1 over 255, and then I would use that dilation parameter. 1 over 255 would be my little delta for t, and I would use that to go from 0 to 2 pi. So I would just basically take what would be 2 times 3, which is like 6, and divide by 255, and I would say that's my delta for radians. I pump it into my my sine wave, and I'd say, okay, let's digitize the sine wave and embody that set of numbers into an array that's 255 elements long. Got to do the same thing for the Gaussian. The two-dimensional Gaussian has to do that in 2D, and other than that, there's nothing particularly remarkable about it. Image processing is almost always going to be involving the digitization of continuous functions. And so we use the Gaussian blur for a few different reasons, but one, I think, which is the most compelling, is its biologically motivated image processing. This is how your brain works. This is your brain on image processing. So inside of your brain, which is an incredibly parallel device, we have large banks of filters. This is a remarkable thing, but it's all built into our biological low-level neurological functions, and we can measure these things by doing these Dr. Mengele-type experiments on cat brains, where we go into the cat brains and we actually measure the output of large areas of neural tissue. They call these things geniculate reticulums, and you can see these horrendous experiments where they take these wires and they put them into cat brains, and then they show the cats, which are kind of dead at this point, these different sorts of patterns, and they can stimulate the neural tissue in their brains. These give you features, and these features create what are called a saliency map, where the saliency map is a fancy name of academics. They have fancy names for simple ideas. A saliency map is a fancy name for the features that are being detected. So it can detect edges that are oriented horizontally, vertically, at an angle, and in fact it can go in increments of 1.2 degrees, and all of this can be detected with electrical signals that are actually stimulated in the geniculate reticulum, going into what's called short-term visual memory. And so that's a remarkable thing, that we can find low-level image processing functions implemented in the biology of our brains. This is even before you get to the part where people start thinking in the cerebellum. This is all stuff you can measure directly. You know, there are these two different things going on inside of our heads, right? There's the brain, and then there's the mind, right? So at the low level, the neurologists can measure what's going on at the microscopic level inside of our brains. That's what neurologists can do. The psychologists, on the other hand, start to talk about the mind. That's the software that runs on the brain. And unfortunately, in the continuum from the microscopic to the macroscopic, there is a big gap in our understanding. How do we get the emergent properties of consciousness, right? These are the things that people say are topics of philosophy, but in fact, sometimes it's topics of artificial intelligence and computer science, right? And in fact, when you think about it, you know, artificial intelligence really is the study of how you can implement an artificial consciousness, right? If you really want to talk about the holy grail of artificial intelligence, it can't just be about fancy search algorithms. It has to be about something a little bit better than that, we hope. But so far, that's all we've been able to get to, right? No one has gotten to the artificial consciousness thing yet. So when you look at this bell curve and you say, yeah, what's the big deal? Well, the reason why that's the big deal is because this is what's going on inside of your brain. And they can do an oriented bell curve, right? You can take it and you can modulate it. You can slide it across the edges and get sub-pixel accuracy. You can do a whole bunch of interesting and wonderful things with the bell curve. But at the end of the day, if you just digitize the bell curve and then do a sliding window product on top of your image, what you're doing is you're blurring the image. And that's it. I mean, no big deal. Low-pass filters blur the image. It's just a question of what function you're using for blurring it. The median filtering, we talked already about that. That's when you take a bunch of pixels and you sort them and then pick out the middle. That's the difference between the median and the mean. And we use the median filter to do outlier detection. We already talked a little bit about how you can implement it with a quicksort algorithm, which is nothing more than a divide and conquer algorithm that's fairly efficient. And then we said, here's the application for salt and pepper images, which is images that contain specks of black and specks of white. You can try and eliminate those things using the median filter, and that can be effective. Where do you see speckled images all the time? Any idea? Any suggestions? Where can I find my speckled images? Magazines. Now, magazine images are pretty good, actually. I think anytime I make a copy, if you make a copy with a copy machine and the glass has got schmutz on it, you're going to have that come across as salt and pepper noise, I think. So here's a median cross filter, and it looks just like the kind of filter you'd use for a sliding window dot product, but guess what? It's not a unity filter, and the reason why is because when you call median on a little cross filter like that, what it's really going to do is piecewise multiply the pixels underneath, then sort them, pick out the middle, and then return that as the answer. So it's not altering the overall amplitude of the image like a mean filter would do, because you're actually calling median on the kernel. The kernel, by the way, that's kernel with a K. That's why I put K in there. So you can call median filter as many times as you like, and it's not going to alter the overall amplitude of the image. We hope. Right? If you think about it, it shouldn't do if you apply the median filter globally. If you did it locally, it might do. And if you want to do it in color, you do it 3 times. One for the red, green, and then blue plain. And here you can see I'm timing it because you're doing that sorting algorithm over and over again. And here it goes. I mean, that median filter does a reasonably good job. Right? Look at the shot noise on this image, and then look at it afterwards. You could still see some pot marks right in here and in there, but in general, the single pixel shot noise has been eliminated. That's not bad, right? Impressive, actually. I mean, imagine if you had to do that yourself, right? Fill in the little dots with some sort of pixel manipulation program. So then the question is, what happens if you use larger kernels in different shapes? Here's an octagon that's a 5x5, and you can become very aggressive removing shot noise. But what you might not see in this projector is that the shot noise is not just removed. The median filter has not just removed the shot noise, it removed the pupils from the mandrel's eyes, because it saw the pupils as being shot noise. And the other thing it did, and I don't know if you could see it, it also removed some of the detail around the cheeks of the mandrel. So it did a few different things here that we would call, I don't know, distortion, artifacts, something. It didn't keep the image as it should have been kept, because you lost a little detail. But otherwise, I mean, it did a reasonably good job of getting rid of what is, I think, a very aggressive salt and pepper noise here. Salt and pepper noise and shot noise are the same. I use the two interchangeably. So median filtering is not free. It costs you computationally. It degrades the image. The question of when you should apply it and where is open. You could make something that is an interactive median filter program, one that sort of looks like a tool that you drag across areas of the image interactively. That might be a fun homework assignment. Well, maybe not so much fun for you, but fun for me. So then there are other things that you can do with your median filter, which I think are fun. You can take the variance, and this is the definition of variance. The variance, that's the square of the standard deviation. So take the local variance of a group of pixels that are underneath the square, and then compute what's called the coefficient of variation, and then use a threshold on the coefficient of variation in order to detect outliers. I call it the dog ate my homework detector, where you get a series of grades from the students, and it could be reasonably good grades, then all of a sudden there's one grade that's really bad because something happened, flat tire or whatever, and I just dropped the lowest grade, and this would detect that. And so if you can find, sort of an outlier, you can drop those pixels. So now, instead of using a pure median filter, you can use outlier detection. So here's before and after a 3x3 with the outlier detection, and I think that's a reasonably good way to preserve, see what happens when you have a small median filter. 3x3 median filter is small. If there is no shot noise contained in that median filter, you don't have to apply it. So if what you can do is you can look underneath where the median filter is, see if there is any shot noise there using the outlier detector, and then apply the shot noise filter, the median filter, only if the shot noise is present. It can be a big win. So if there's occasional shot noise, it's really good to know that you don't need the median filter at certain points. So knowing when to apply the median filter, as opposed to making an interactive tool, making an automatic tool for applying the median filter, that just sounds so important and good, right? Because I don't need to globally median filter the whole image. I could just be very selective about it. Say, oh, look, there's shot noise. Let's use the median filter. So if I can be good with detecting these things, that's helpful. A high-pass filter is kind of computationally identical to the low-pass filter. It just has a different format for the image. And what that'll do is it'll sharpen things up, right? So it's giving us kind of like what I would call a difference between adjacent pixels. And so this is how I do the high-pass filter kernels. I like to normalize them so I don't change the amplitude of the image. I want to add up all of the well, what could happen if you add these things up and it adds up to 0? If I add up everything with, there's negative numbers here. If I add up all the numbers and it adds up to 0, I can't just divide through by the addition of all those numbers in order to effectively create a unity filter, because it would mean dividing through by 0, and if that happens, my eyeballs turn black and fall out. And I know that's true because I learned math on the street. So I better not divide through by 0. Instead, what I do is I call a normalize function, and so what that does is a safe kind of detecting of the total in the matrix, and then if it's not 0, it'll proceed to divide. Then when I do my convolution, that'll detect, that'll emphasize changes in energy. And so this is what it's doing. It's taking a derivative, a local derivative, by taking the difference between adjacent pixels. And that's also amplifying noise. So in general, before you apply such a filter, if you want to be reasonable about the kinds of edges that will be detected after you apply the filter, you first do a low-pass filter, then you look for the sudden changes of noise, and then you do a threshold detection. And that's how you normally do edge detection. So why is that true? Well, the reason why is because when you take a derivative, if there's a sudden change in a function, the derivative is not well defined, right? You need a continuous function. That is a function with a, well, think about it a different way. There's different kinds of continuity, right? C0 continuity means that the functions are always touching, right? So if you think about it, a square wave does not have C0 continuity because it starts at 0 and then suddenly changes to 1, right? That would mean, I think, almost certainly the derivative is not defined, right? C0 continuity isn't present. But you could have C0 continuity present if you have a triangle, right? The apex of the triangle is touching the other apex of the triangle, but the sudden discontinuity of the derivative, the first derivative, means you have C0 continuity, but you do not have C1 continuity. So with C1 continuity, you have a continuous smooth curve for the first derivative, so it exists. Now, if you think about it, you could have certain kinds of curves that have C infinity type continuity. For example, a sine wave. You could take a sine wave's derivative as many times as you like, and it will still have an existence, right? Derivatives exist no matter how many orders of derivative you take. So when you think about it, to make things well conditioned in your image before you take your derivative, you want to run that low-pass filter. Otherwise, you could have low-level discontinuities that make the derivative undefined. And so you're looking for that C1 continuity inside of the image in order to have a well-conditioned input in order for you to be able to take a derivative. So what I like to do is I like to run some kind of low-pass filter. Could be a simple average, could be Gaussian. And then I'd like to be able to take my derivative. So here's a nice image. Here's salt and pepper noise. This is just impulse noise, which is just salt. And here's Gaussian noise. And you can see the different kinds of noise are really different in my view. I don't know if you can see it so good from where you're sitting on the projector side. Is it obvious that these are different kinds of noise where you're sitting? You can see it, right? Not so good, but it's there. So here's that sort of 3x3 mean filter, and I'm going to say that does this work? It's sort of working. That's a 3x3 mean filter, so they're all ones. And then you divide through by a ninth in order to normalize. And now here's the mean filter. 3x3, 5x5, and 7x7. Gaussian noise, salt and pepper noise. I see an image that's losing some of this noise, but is also getting blurry in the result. I find these kinds of filters just make blurry images. That's what they do. But they also condition the image so that I can take a derivative. Let's see what else we can do with this. Some more filters. This is, I don't know if you can see it, that's a square, and that's supposed to be an image of a Gaussian function, and it's actually done to scale. So this is the size of the kernel that's being used on the image underneath. And here's the actual original image off on the left, and you can see there's a ton of detail in here. So now I take my low-pass filter and I run it through, and you can see artifacts coming through. You can see little lines running through the image that have been emphasized by the fact that this has a square edge to it. Whereas here, and using this so-called Gaussian filter, those edge artifacts are missing. And now the question becomes, what would happen if I were going to edge detect it? Well, we would see these large changes of energy here. We'd be missing all of the low-level background noise. but we would still get some of the areas where there's like bundles of twigs. Those would come out, and we would get these blobs, and the blobs would make edges. So you're making large, I'll call it a blob detector when you start low-pass filtering these things. So then comes the question, all right, how do I implement all this good stuff? And, well, this is how I go about, coding a Gaussian function. So let's go back and look at it for a second. Here's the Gaussian function right over in here. You can see it's an exponential. It's missing the part where the x sub c, y sub c is at. It's got the little sigma over in here. Now if you go back to this little doodad, it's the here's the x squared plus y squared, where you can see x and y squared are being computed. And here's the x sub c, y sub c getting encoded. And at the end of the day, what you're going to end up having to do if you're going to digitize this thing is you're going to have to get a doubly nested for loop and change x and y so that it sweeps across the kernel in order to generate the different values. And I do that. Here's a nice function right here in the corner, so you can see it. I guess they call it code for a reason. I mean, I can see the basic principles obviously when I look at the math, and then when I look at the code I go, how did they get this? And you can sort of see it's in there. Did people kind of see the implementation is sort of working? You can see here's the e part right in here. And then here's the minus x squared plus y squared up in there. And now it says here it's being multiplied by 1 on sigma 2, where sigma 2 is sigma squared. And then that's divided by 2, so I don't know. It's kind of wacky. Should it be multiplied by 2 or divided?
You have 1 over sigma 2 and then multiplying, so.
Yeah, I guess it works. Anyways, here's what I do inside of one of my subroutines. IPL update basically makes a new instance of an image by calling on this smoothing processor. And you have to do things like parameterize these filters. So you want to add a link so that sliders can adjust sigma, a link so that sliders can adjust the width of the kernel. I like to make the width and the height of the kernel the same. So I personally, I don't see any point in having a Gaussian function that's narrower than it is wide. So I assume that we're dealing with a matrix where width and height are the same. So I just say, give me the width, and I'll just assume that's the height. And then something on the order of sigma. If sigma is given in as a large number, but you don't have enough width or height, the large number is just going to take the bell of the curve and spread it out so far that you won't see any tapering. So you've got a bit of a trade-off in terms of the size of the kernel and the sigma. Not only that, there's another factor in this when you implement it. If you have a large kernel, it takes longer to do the image processing. I don't know, mathematically, that shouldn't be relevant, but practically, it's very relevant. So if you want to go and implement these things with a large kernel, and let's say it's, what's large? Say 31 by 31. That's not particularly large. But even with the fastest subroutines in Java Advanced Imaging, assuming you're not using FFTs, that kind of a convolution could take you like a second on a 1024 by 768 color image. So that's a substantial amount of compute time. That means you can't do it in real time if you're using naive convolution. So here's another interesting artifact, right? There's that border. Look at that. The image is, dare I say it, shrunken, right? Because why? Because the border is not well defined at the edges. And unless you implement wrapping where it wraps around from the other side and comes up, assuming that you have a replicated image, which this isn't, and that's replicated forever, then you really don't have a good way to define the border. So normally when you use the accelerated version, the Java Advanced Imaging Subroutine libraries, which do the fast convolution, they chop out the border. If you implement it yourself, or if you extend the image and make it a little larger so that it won't have a border by putting in replicated pixels, then you can preserve the image. But then the question becomes, where are you supposed to get the extra border? Right? You're supposed to grab it from the right side and wrap it to the left? Well, that's what I do, but that's not necessarily the right thing. Got lots of choices. Faces. Faces are biological signals, you know. This is biological, right? This is still biomedical imaging because we're dealing with faces. So if I work with faces, it's biomedical imaging. So what can I do with these Gaussian blurry faces? Oh, look, blurry faces. Oh, how wonderful. Ooh, how blurry. Well, I could run them through an edge detector, right? So here's my little edge detector, and it's thresholded, and that looks like something. I could almost see taking that and making it into art. Etching it with my laser cutter, right? You can do that. But I wanted single pixel width wide edges. I don't want just these large areas because the laser cutter's, got to have a place to go. So what I do is I run what's called a Sobel. This is a Laplacian of Gaussian, and then a Sobel edge detector on it, and then I get my my single pixel width wide edges, and that's my shtick. And so what I thought I would do for like a good time is run my little Java program over in here and kind of show you how all of that stuff works. So you can change the thresholds, you can change the kernel width, oops, and what we'll do is we'll open the original image, and we'll play around a little bit with the Gaussian panel, and you can see the blurring happening, and you can see the length of time it takes to apply on a large kernel image. Now check it out. If I reduce the kernel size, things start to work pretty quick. But if I want a little bit more blur, I better increase my kernel, and now things are slowing down quite a bit. Not to put too fine a point on it, but at the end of the day, I print out how long it takes to do the convolutions. And if you wanted to, you could make those kernels rather large, and they would be very slow. Let's see how large we can make these things. So that's a 1 second process with a 40 by 40 kernel. What do you think of that? Cool, right? Works. sort of. So if you wanted to, we could pick an image and work with it. Let's capture the screen. Oh no, if I capture the screen, I'll be capturing the image itself. Let's try a different image. What shall we use? I use the baboon a lot. Here are peppers. They're nice and colorful. And it's a reasonably small image. So let's start with that. That's a good image. What shall we start? What shall we do first? Any ideas? Want to make a grayscale image out of it? Or shall we try quantizing the image? We'll re-quantize the colors and reduce the total number of colors in the image. Let's start with a median cut algorithm. So here's the difference between 8 and 32. I'm starting to get shadows. Let's make that 64 colors. We'll apply the change, and then what I'd like to do is a histogram equalization, just to brighten things up a bit. So this is a uniform non-adaptive histogram equalization I'm doing now. Sometimes I think image processing is a bit of an art, because you kind of have to try things and see what works for your image. So now with the histogram equalization, I can go back to my median cut algorithm and see what happens. I think that's about all I can get. I'll just leave it the way it is. How about we make this into a grayscale image and then apply it. So how's that? You can do the unihe. That looks pretty good. Let's apply it. So now I've done my color quantization, my uniform non-adaptive histogram equalization. What's next? Remember, I'm looking for good edges, but I need a decent contrasted image. So can I do something to improve contrast?
High-pass filter.
Well, high-pass filters don't necessarily do contrast. I don't have to do a uniform non-adaptive histogram equalization. This is an exponential histogram equalizer over here. I have other things I can do to adjust contrast. There's a contrast panel, right? Contrast panel lets me adjust brightness. Lets me adjust contrast. It's all interactive. Does that help us any? I think a high contrast image with low overall brightness gives us some reasonable edges. Not too much noise right there. What do you think of that? Does that help? I'll let you be the judge. If it doesn't help, we don't have to use it. Let's look at some of these other filters. You were suggesting a low-pass filter. I have a thing here that says Show Filter Buttons. Show Filter Buttons iteratively traverses the entire submenu and constructs a panel consisting of buttons. Each button has correspondence with a single menu item. So if it's a menu item, it'll turn into a button. So Show Filter Buttons will be huge. Right? That's big. Maybe too many. But I have Show Filter Buttons available in many of the submenus. Right? So for example, if you go into filter, low pass filter, it shows low pass filter buttons. So here, is a usable subset of the menu items that are in the low pass filter. So I can try these things without applying them just to see how they look. Just a quick click. There's a Gabor filter. Here's an average filter. And there's a mean filter. You can see it's kind of looking a little blurry with the mean filter. There's a blur button panel, which could have just as well have been in the low pass filter. And now let's see, here's something called Gaussian panel. And now with the Gaussian panel, I'm back to changing the kernel width, only it's interactive. And you can see the width, the actual width of the kernel in the border. That's a 40 pixel width wide kernel with a small image. It runs pretty quick. So we can make a nice big kernel, and then we can change the aggressiveness of the kernel by increasing the standard deviation of the Gaussian. So now we actually get to visualize the bell curve and its power in terms of making things blurry. Right about in here, I could probably reduce the kernel size. That improves the overall number of pixels that I'm able to see. And I will apply that filter. Now, having done all of that, I had to make a judgment about what the large areas were that I wanted to keep in order to create my outline. And what that says to me is my brain is not just doing low-level image processing. I'm allowing my thinking about the image to interact with my control. So as I change the parameters of the filter, I am making a decision about what looks good. If it looks good, go with it. That's the way I see it. Image processing textbooks don't talk about this, right? They don't talk about the art of doing image processing. They don't say, well, pick the sigma that looks best. They don't even tell you how to pick the sigma.
Now light goes.
Beg your pardon?
Now light goes.
Is that how, what now?
Light goes. Light. Real light.
Is that how real light goes?
Is that how real light goes?
Oh, that's how real life goes. Yeah. Well, I mean, the textbooks that you get in image processing can tell you the underlying detail of the algorithm. They can tell you the math, but they can't tell you something like, what's going to work for your image. That they can't tell you. So you need, wouldn't it be nice if it could? Wouldn't it be nice if this were totally automatic? But there isn't a way to do it. So I made a judgment based on what I wanted to do with this image, which was to run it through a laser cutter and try and get large areas of reasonably constant intensity. So if that were a criteria, and if that were something that you just wanted to try and measure, you could maximize that by saying, oh, look, I can get large areas of reasonably large intensity, and I can maximize that. Look, I'll just make the whole thing blurry. And then there you go. And now we're done. But there's a trade-off, right, between getting large areas of large intensity and losing detail, losing all detail. Eventually what will happen is you'll have a filter so aggressive, it just takes the whole image and turns it into a constant number. It makes the whole thing just one big blur. And so there has to be something in there beyond the criterion of optimality that says we want blobs to be as large as possible, because we still want them to be distinct enough to represent the object of interest. So the question then becomes, how do you trade off blob size against loss of detail. And there has to be some trade-off in there that lets you say, you know what, this looks a little bit better when it's a little less blurry. So I would keep that over making it like a totally blurry image. And then comes the high-pass filtering. Here's a bunch of high-pass filter buttons. Not too many. And I got edge detection buttons. And now we can show them all. And here's a bunch of edge detection buttons. And these are oriented Robinson filters, edges that are oriented in any one of 8 directions. Here's a Laplacian Pruitt filter, which is kind of looking pretty good actually. And this is a Mexican hat filter. Mexican hat's just like a Gaussian, only you take the Laplacian. No, it's the derivative of the Gaussian. It's a dog filter. Derivative of Gaussian. Oh, don't do the Huff transform. Oh no, what did I just do? Sorry. Let's go back. Filter, edge, show edge buttons. Harris, Laplacian of Gaussian. Here's the magnitude of the derivative of the Gaussian, magdog. There you go. This is a Laplacian of Gaussian with a Sobel. And you're getting nice single pixel width wide edges with Sobel. And now what we'll do is we'll reduce the kernel width in here. And we're losing some detail. But you're getting some nice outlines. So you're trading off detail in the image for the outlines. It looks like there's a trade-off here. Apply. Now I could turn off the threshold part. Or I could turn off the Sobel part. Actually, that's not bad. But I like the Sobel part because that gives me the single pixel width wide edges. So if you have thresholded the image and you want the thresholds to turn into single pixel width wide edges, run a Sobel filter on it. That's actually good to know. So there you go. Huh? Can't tell what it is anymore. So maybe I did a little too much image processing. Little too much.
Art.
It's art. Doug's art fart. So what I'm thinking here is, how do I connect this to my laser printer, my laser cutter? Well, the laser cutter is an interesting device. The laser cutter is different than any printer that you're normally going to encounter. The laser cutter is more like a pen plotter than it is like a laser printer. And let me tell you why. The laser cutter has the ability to turn the laser on or turn the laser off, and the laser cutter can move the laser in the X direction and in the Y direction. And that's what the laser cutter does. And that's it. A pen plotter has the ability to take a pen and put it down or pick it up. And the pen plotter can move the pen in the X direction or it can move it in the Y direction. So a laser cutter is just like a pen plotter, only it's drawing with a laser that can cut through plastic, and the pen plotter is drawing with a pen. And other than that, they're both vector output devices, and they both use precision stepper motors in order to be able to position the output device in well, I guess on what you would call the Cartesian coordinate plane. That's what they do. That's it. Now, what you have here is a set of pixels in X and Y. Some pixels are on, and some pixels are off. But none of them represent a vector. None of them will tell you, go to this location and fire your laser. And so what you want to do in a case like that is have a series of line segments that are created from the edge detected image, and those line segments ideally would be connected. Connected line segments would enable the laser, when it's on, to continuously draw. Disconnected line segments would require that the laser turn on here, and then turn off, then turn on next to it, and then turn off, then turn on next to it. It would be, what a pain. It would never finish drawing. So the same thing would happen with a pen plotter. In other words, what you have here is a raster, and what you're looking for is a vector. And so what you need to do is raster to vector conversion. Raster to vector conversion means taking the collection of pixels that are on and concatenating them into a series of vectors with the endpoints known. Raster to vector conversion is just the first step, however, because if you have a series of vectors that are not connected, then your laser will take forever to do its cutting. So your post-process to the raster to vector conversion includes vector ordering. Now, vector ordering is interesting because it's NP complete. And what that means is it's as hard as any problem in NP space. What that means is it's as hard as the traveling salesman problem. And in fact, the vector ordering problem is also termed the Chinese postman problem, a classic problem in computer science. In the Chinese postman problem, what you're attempting to do is deliver the mail without visiting any mailbox twice. And you're trying to do it in a reasonable order, maybe one that minimizes the amount of time it takes to deliver all the mail. So as a result, ordering the vectors could take substantial time, but we're okay with that because it's pay now or pay later, and your laser will pay later in a big way because the amount of hours that you have on your laser tube will determine when the laser tube needs to be replaced, and that laser tube is terribly expensive. So it'd be really good if we could minimize the amount of time the laser tube spends on, and it would also be really swell if we didn't have to keep turning the laser tube on and off all the time, because the laser tube is stressed out when it keeps getting turned on and off all the time. So we've got a couple of problems here with our laser cutter. We want to minimize on time, and we also want to minimize what I would call the amount of time we turn it on and off rapidly. That is, minimizing duty cycle stuff. So ordering the vectors seems like a really reasonable thing to want to do. Tough problem. And what do we do after we order the vectors? Well, here, let me show you something. You're going to love this. I wrote a drawing program some time ago, and it's under Chapter 26, Graphics, and it's called Draw Main, and it's in Chapter 26, Draw 2D. And when you run draw main, it lets you draw using vectors in Java. And here's my little drawing program. Here's a little ray. And if you want, you can draw, here's a circle. Isn't that cool? And you can even fire the ray through the circle and refract it. So it lets you do what's called transmission and reflection, assuming there's an index of refraction that causes the ray to bend when it passes through the surface of the presumably glass sphere. And it bounces around and comes back out. Okay, and what does this have to do with the laser cutter, you ask? Oh, I'm very glad you asked me that. So what I can do with my little program is I can export my vectors into what's called SVG format. And I'm embarrassed to tell you I'm drawing a blank in terms of telling you what SVG stands for. I think it's Scalable Vector Graphics. Something like that. SVG, you could Google it for me if you don't mind. I think that's right. I'm close. So I'll save this circle as circle.svg. Oops. I was correct? Scalable Vector Graphics. So now if I go into save this, I can quit out of Java completely. Done with Java. And I can start a program which is available on the Mac, Windows, and Unix, and is open source. And this program is called Inkscape. Now, Inkscape is able to read SVG type files, scalable vector graphics files. So if I open my circle, where is it now? It's under J for P, data. Where did I do with it? Oh, it says all Inkscape files. I want all files, or all SVG files. How about all vectors? All files. What did I just do with this darn thing? Oh, here it is. No, that's foo. I know I did something called circle, right? There it is. I lost it. Huh. Silly me. So here is a file that was created by my Java program. And there's a magnifying glass in here, and you can zoom in on it. So, then the question is, how do you know this is a vector? Well, if you can ungroup the object and then take individual elements and drag them around, you know it's a vector, right? So as you can see, this is a vector. See? See? Vector? Not a bitmap. Like that. There's a tangent. I can do a thing over here. There's a little circle doodad. I could probably change fonts. I'm thinking maybe. Let's see, what happens if you ungroup this object? Ungroup. Does that work? I'm not sure what I just did. Oh, that's not the, this is not the droid I'm looking for. Well, I'm totally screwing up my little picture. But that's okay. I don't care. Can I ungroup this? Ungroup. Yes. No. I'm not exactly sure what it is I can and can't do in Inkscape, but it doesn't quite matter yet. I'm very new to this program, and the only reason I'm using it is because you can do this, print. And when you print, you can print to an XPS document. Somebody tell me what XPS stands for. That's like a Microsoft thing, right? If you print to XPS, you get a prompt, and now I got circle.xps. Did somebody Google XPS? Something, it must be XML PostScript or something, right? It's a Microsoft thing. So once you've got your XPS document, you can run a program which I happen to have for the laser. Did you find it, Brian?
Yeah.
What's it called?
It's an open specification for a page description language, and it's XML based, more precisely XAML based, based on a new print path and a color managed vector based document format that supports device independence and resolution independence.
So PS is supposed to be like PostScript. X stands for XML.
Page description.
Oh, page description language?
Paper specification.
So who is in charge of this spec?
Microsoft.
Okay, so it's proprietary Microsoft format.
And ECMA International.
ECMA, who's that?
European Computer Manufacturers Association.
Oh, okay. So it's actually a bona fide standard?
Seems to be.
Well, I found that I couldn't generate XPS documents on a Mac easily. But if I'm on Windows, I could. But it doesn't matter because I'll deal with SVG because that's what everybody else uses. That's the standard that I know that's open and not Microsoft. But once you have a XPS document, the laser program will open it. And so here's Circle XPS. And there it is. Now the colors, if you have different colors, you can change whether you have them rendered by cutting or rendered by what you might call etching, right? You can change the power for each color. So if I find, oh yeah, here's a color that's yellow in here, I can change the power down to something that won't cut all the way through, that'll just draw the text or something. So I'll give it like 10% power. What that'll do is it'll just kind of carve out a little trough in the plastic. So if you have colors, it'll preserve them. You can change the speed and power for the different colors. That's really the only thing you can do with the laser is change speed and power. Here's the yellow outline, and here's the black, and this one is saying that the black will be done at full power and the yellow is done at 10% power for whatever reason. So I can basically move the laser around. I've got buttons for jogging it. That's what makes this important software for me. I can jog up and down. I can move the platen up and down. I can do a little bit of design in the design view, but I think most of my design will be done elsewhere, perhaps in Inkscape. It's a more robust program, has many more things that are interesting. But that's the bird's eye lowdown on the laser caper. Oh, and here's what I made with it. I had an old CD cover, and I decided to try and sort of burn my way through it at full power, at full speed, and I'll just pass this around. It'll cut through much thicker plastic than that, and using full power on it was probably not the brightest thing in the world, but I figured, what the heck, let's go for it. here's a little case that I was working on.
So the E and the O.
Yeah, I kind of blew away some of the. Yeah, this case, I don't know if you can see it well, but this is one of those cases where the pieces over in here are meant as slots, and what you do is you try and form edges which have little places that go into the slots, like over in here. You can see this edge comes in. When that gets cut out, it'll mate with the slot. And you can cut in holes. You can see these holes in here, the blue ones. That's for a USB jack. The square one, that's for a Ethernet. The round one, I think that's going to be for an audio jack, and this is going to be for a power jack. Basically, I wanted to build a little plastic acrylic case for my my little Kickstarter project. Oh, and the other thing is, once you have these things debugged and working, you can send them out for manufacturing. So what that means to you, there are other ways you can do synthesis of cases when you go to make things, right? You can use a 3D printer. That's true. But the 3D printer is not going to allow you to manufacture in quantity. That's very good for making one, but it's not really good for making lots. The only way to make lots out of a 3D printer is to use the prototype to make a mold. Unfortunately, if you make an injection molded plastic mold, you're dealing with about $3,000 for the bottom half and another $3,000 for the top half. So by the time you're done with engineering costs and your mold making, you're probably into the device for a good $6,000 to $10,000. And then you can produce it out of engineering plastic. Engineering plastic per pound costs as much as a gallon of gasoline because it's a petroleum product. So as the cost of gas goes up, the cost of the plastic goes up. But so that makes it great. I mean, you can probably make your I don't know how much you'd sell it for, but you'd probably have to make about $10,000 in profit before you break even. And to make that happen economically, you've got to sell a lot of whatever it is you're selling. So with this kind of opportunity, you can fabricate your costs will probably be something for a reasonable sized box of something on the order of let's say $7 a box if you're making 100. But then making 100 is a reasonable proposition, and you can turn it around and sell your box for $15 or whatever. Add $7 to the cost of goods for when you go to sell your device. It'll be in a proper case. So one of the nice things about that is when you outsource, they'll fabricate it properly and you'll make a lot of them, and the costs aren't too terribly high in terms of startup costs. I think the one-time startup costs are what really kill injection molded plastic, especially for products that we might take to Kickstarter, because we don't normally envision selling tens of thousands of things on Kickstarter. Yeah, like Arduino guys, they're typically small. My entire thesis is that the numbers don't justify it when you go to make injection molded plastic, unless, I don't know, you can find a way to justify the startup costs. Is it break time? I think we need a break. Shall we take a break? Okay. So when we come back, we'll finish up by talking about how we can do the edge detection.